Tonight, we shall embark upon a journey of profound melancholy, a voyage not across space, but across time. We are turning our gaze to our celestial neighbor, the red planet. To the modern eye, Mars is a desolation. It is a world of rust and dust, a frozen desert where the silence has endured for eons. But it was not always so. There is a ghost haunting the craters of Mars. If we wind the clock back, drifting through the mists of 4 billion years, we find a world that shocks the imagination. We find a twin. Tonight, we visit the Mars that should have been, the blue marble that orbited alongside our own, teeming with the promise of life before the lights went out. Let us descend through the atmosphere of this ancient world. It is the Noachian period, named after the biblical flood, and the name is fitting. As we break through the clouds, thick, heavy, cumulus clouds laden with moisture, we do not see a red landscape. We see gray, rocky continents, battered by impacts, rising out of a vast, steel-blue sea. This is the Oceanus Borealis, the Northern Ocean. It covers nearly a third of the planet's surface, a body of water deeper than the Mediterranean and wider than the Atlantic. It laps against the shoreline of the dichotomy boundary, the great cliffs that separate the northern lowlands from the southern highlands. Listen to the sound of this ancient world. It is not silent. There is the roar of the wind, thicker and heavier than the thin breeze of today. There is the crash of waves against the basaltic shore. There is the sound of rain on Mars. It falls in sheets, washing the dust from the air, carving gullies into the crater walls, gathering in streams that merge into rushing rivers. These are not the flash floods of a desert, but persistent, meandering rivers that flow for centuries, carrying sediment and sand to the sea. We are standing on the edge of what will one day be known as Jezero Crater. In our time, it is a dry, dusty bowl. But here, 4 billion years ago, it is a lake, a magnificent crater lake, filled to the brim with fresh water. A river breaches the crater wall, cascading down in a waterfall that thunders into the basin. We can see the delta forming, a fan of fan-shaped sediment deposits where the river slows and drops its load of silt. This mud is rich in clays, smectites, and phyllosilicates, minerals that can only form in the presence of liquid water. They are the chemical fingerprints of a wet world, and they are forming right now beneath our feet. The air we breathe here is different from Earth, but it is substantial. The atmospheric pressure is high, perhaps even higher than on Earth today. It is a blanket of carbon dioxide, nitrogen, and water vapor. It creates a greenhouse effect, trapping the heat of the sun. This is crucial, for the sun of this era is the faint young sun. It burns with only 70% of its modern brightness. Without this thick, insulating blanket of gas, Mars would be a ball of ice. But the atmosphere holds the warmth, keeping the surface temperature above the freezing point of water. It is a delicate balance, a thermodynamic tightrope walk that allows the liquid miracle to exist. Look up at the sky. It is likely not the deep blue of Earth, but a hazy, pale violet or perhaps a creamy orange, colored by the scattering of light through the carbon dioxide and the suspended water droplets. It is a sky that promises weather. Storm fronts move across the horizon, driven by the planet's rotation. Mars rotates once every 24 hours and 37 minutes, a day almost identical to our own. The similarity is haunting. If you were an astronaut standing on this shore, watching the sun set, your circadian rhythm would feel perfectly at home. You are on a smaller Earth. The geology of this young Mars is violent and active. The Tharsis region, a massive bulge in the crust, is beginning to rise. Volcanoes, the ancestors of the giants we see today, are erupting. But these are not just lava fountains. They are interactions between fire and water. Lava flows pour into the ocean, creating massive explosions of steam, sending plumes of ash high into the stratosphere. This volcanic activity pumps gases into the air: carbon dioxide, sulfur, methane, replenishing the atmosphere and maintaining the greenhouse warmth. The planet is geologically alive. Its heart is beating, driving the tectonic shifting of the crust. Consider the water itself. It is not pure, distilled water. It is a chemical broth. It is salty, rich in dissolved iron and magnesium washed down from the volcanic rocks. It is slightly acidic, perhaps, saturated with the carbon dioxide of the air, but it is the universal solvent. It is the medium in which chemistry becomes biology. In the quiet, shallow lagoons of the crater lakes, molecules are bumping into each other. Amino acids, brought by comets or synthesized by lightning strikes, are linking up. Lipids are forming bubbles. The primordial soup is simmering. Did life begin here? It is the question that haunts every rover we send. The conditions are perfect. In fact, some planetary scientists argue that Mars might have been habitable before Earth. Earth, at this time, was still reeling from the impact that created the Moon, a magma ocean cooling slowly. Mars, being smaller, cooled faster. It settled into a habitable state millions of years before its larger sister. It is entirely possible that the first DNA in the solar system coiled itself in the mud of a Martian lake. We may be looking at the true cradle of life. The surface is also being shaped by violence from above. This is the era of the late heavy bombardment. The solar system is still cleaning itself up. Stray asteroids and comets, disturbed by the migration of the gas giants, rain down upon the inner planets. We see streaks of fire in the sky day and night. Impacts shatter the crust, creating the basins like Hellas and Argyre. But these impacts are also bringers of life. The comets deliver water and organics. The heat of the impact craters creates hydrothermal systems, hot springs that last for thousands of years. Warm oases where microbes might thrive even in the depths of winter. Imagine standing on the rim of the Hellas Basin just after its formation. It is a hole in the world, 9 kilometers deep. The atmospheric pressure at the bottom is immense. It is warm enough for water to boil. It is a crucible. Over time, it fills with water, becoming a circular inland sea the size of the Caribbean. Clouds gather inside the crater walls, trapped in their own weather system. It is a world within a world. The seasons on this ancient Mars are extreme. The planet's tilt, its obliquity wanders chaotically over millions of years because Mars lacks a large moon to stabilize it. At times, the poles are tilted directly at the sun, melting the ice caps completely. At other times, the planet stands upright, and the equator freezes. The biosphere, if it exists, must be adaptable. It must migrate. It must learn to hibernate in the mud when the freeze comes, and bloom when the waters return. It is a challenging environment, but life on Earth has survived worse. Let us walk along the valley networks. These are not the short, stubby gullies of later eras. These are dendritic systems, branching like the veins of a leaf or the capillaries of a lung. Look at the patterns in the rock. They tell us of sustained flow. They tell us of a water cycle. Evaporation from the ocean, condensation in the clouds, precipitation in the highlands, and runoff back to the sea. It is the heartbeat of a living planet. It requires a thick atmosphere to support it. It requires a protection that we take for granted. The duality of this vision is stark. We look at the rover images today, the Curiosity rover in Gale Crater, and we see layered sedimentary rock. We see mudstones. We see cross-bedding, the petrified ripples of an ancient stream bed. These are not hallucinations. They are hard geologic facts. The stones of Mars are screaming the truth at us. We were wet. We were submerged. To deny this former world is to deny the evidence of our own eyes. But there is a subtle darkness in this beauty. The sun is dim. The warmth is fragile. It relies entirely on the greenhouse gases. If the volcanoes were to stop, if the carbon dioxide were to be scrubbed from the air and locked into carbonate rocks, the temperature would plummet. Mars is living on borrowed time. It is a small engine compared to Earth. It has less gravity to hold its atmosphere. It has less internal heat to drive its geology. It is balancing on the edge of a cliff, and it does not know it. We see the first signs of the coming ice. In the highlands, glaciers are growing. They carve U-shaped valleys through the mountains. The water cycle is beginning to slow. The ocean levels fluctuate. There are periods where the planet dips into a snowball Mars state, covered in white, only to be rescued by a burst of volcanic activity. It is a struggle between the internal fire and the external cold. For now, in the Noachian, the fire is winning. The water flows. Imagine the nights on ancient Mars. The stars are the same as on Earth, though perhaps slightly shifted by 4 billion years of galactic rotation. Phobos and Deimos, the two tiny moons, hurry across the sky. Phobos rises in the west and sets in the east, moving faster than the planet spins. It is a jagged, potato-shaped rock, a captured asteroid. It creates no grand tides like our moon. It offers no stabilization. It is just a passing spectator to the drama below. The reflection of the stars in the calm waters of a Martian lake is an image of profound peace. It suggests a universe where life is common, where blue worlds are the norm. It suggests that Earth is not a lonely freak, but part of a family. If we had arrived then, we could have taken off our helmets. We might have needed oxygen masks, as the air was likely CO2 heavy, but we would not have needed pressure suits. We could have walked on the sand in shirt sleeves. We could have dipped our hands in the water and felt the chill of a living world. This is the tragedy of the story. We fell in love with the corpse. When we finally reached Mars with our probes and our robots, we arrived 4 billion years too late. We missed the party. We walked into the ruins of a great civilization, not a civilization of buildings, but a civilization of chemistry and hydrology. The grand experiment had already ended. The lab had been burned down. As we leave the Noachian period, the clouds are beginning to thin. The rain is becoming less frequent. The Great Northern Ocean is retreating, leaving behind salt flats and drying mud. The planet is changing. Something is happening deep beneath the surface. The engine that drives the protection, the magnetic heart of the world, is faltering. The invisible shield that holds back the solar wind is weakening. We have seen the paradise. Now we must witness the fall. The story of Mars is not a story of a world that never had a chance. It is the story of a world that had everything: water, warmth, atmosphere, organic chemistry, and lost it all. It is the story of a planetary death. And to understand the murder, we must identify the weapon. The weapon was silence, the silence of the core. The sky above is darkening. The faint young sun is indifferent to the fate of the rock circling it. The wind picks up, but it feels colder now. The warmth is leaking away into the void. The mirror world is about to shatter. We have walked the shores of the ancient Martian ocean, feeling the spray of a water cycle that has long since vanished into the vacuum. We have breathed the thick, warming air of the Noachian period. But to understand why this paradise existed, and why it was destined to die, we must leave the surface. We must look past the crashing waves and the erupting volcanoes. We must journey downward, through the red regolith, through the miles of basaltic crust, and into the crushing darkness of the planetary interior. For the true hero of this story is not the water nor the air. The true hero is a churning, violent engine of liquid metal buried 2,000 kilometers beneath our feet. Imagine stripping away the skin of the planet. We peel back the crust, a rigid shell of rock that varies from 20 to 50 kilometers in thickness. Below it lies the mantle, a vast layer of silicate rock, hot and viscous, moving with the slowness of geologic time. It is a plastic solid, flowing like candle wax under pressure, carrying heat from the deep interior to the surface. But we must go deeper still. We descend into the core. Here, the pressure is immense, millions of times greater than the atmosphere at the surface. The temperature climbs to thousands of degrees. We have reached the foundry of the world. In the center of ancient Mars, just as in the center of Earth, lies a sphere of iron. But it is not pure iron. It is alloyed with lighter elements, sulfur, nickel, perhaps a touch of oxygen. In this early epoch, 4 billion years ago, a significant portion of this core is liquid. It is a molten ocean of metal, a hellish, glowing fluid that seethes and boils. This is not a static pool. It is in constant, chaotic motion. Heat, trapped from the formation of the planet, is trying to escape. It drives convection currents. Massive plumes of superheated iron rise from the center toward the core mantle boundary, cool slightly, and sink back down. But there is another force at work: rotation. Mars is spinning. It completes a revolution every 24 hours. This spin imparts a twist to the rising and falling plumes of iron. It is the Coriolis effect, the same force that makes hurricanes spin on Earth. In the core, it twists the convection currents into spirals, into helical columns of flowing metal. Now, remember your high school physics. Iron is a conductor. When you move a conductive fluid through a magnetic field, you generate an electric current. And when you generate an electric current, you create a magnetic field. This is the dynamo. It is a self-sustaining feedback loop. The magnetic field creates the current, and the current reinforces the magnetic field. It is a magic trick of thermodynamics, turning the kinetic energy of the spinning, boiling iron into a force field that extends far beyond the planet itself. Deep in the dark heart of Mars, this engine roars silently. It transforms the thermal energy of the birth of the world into a protective cloak. Let us return to the surface, but with a new vision, the vision of a magnetometer. We see lines of force erupting from the south pole of the planet. They loop high into space, curving around the equator, and dive back into the North Pole. It is a giant invisible torus, a donut of magnetism that encases the world. This is the magnetosphere. To the naked eye, it is nothing. To the solar wind, it is a stone wall. The sun, even the faint young sun, is a violent neighbor. It constantly spews a stream of charged particles, protons and electrons, traveling at supersonic speeds. This is the solar wind. Without a shield, this wind would slam directly into the atmosphere, stripping away atoms, breaking molecules, and sterilizing the surface. But the magnetosphere stands in the way. When the solar wind encounters the magnetic field of Mars, it is deflected. It flows around the planet like water, flowing around a boulder in a stream. The particles are shunted harmlessly to the sides, passing by the planet and continuing into the outer solar system. Inside this magnetic bubble, the atmosphere is safe. The delicate molecules of water vapor, the carbon dioxide that keeps the planet warm, the nitrogen, they are protected from the stripping power of the sun. The pressure remains high. The greenhouse effect holds. The ocean remains liquid. The dynamo in the deep is the guardian of the paradise on the surface. Without the churning iron, the water cannot exist. The biological potential of the planet is entirely dependent on this invisible physics. We can see the evidence of this shield even today, fossilized in the rocks. In the late 1990s, the Mars Global Surveyor spacecraft orbited the planet. It carried a magnetometer. It found something that stunned the planetary science community. In the southern highlands, the oldest crust on Mars, there are stripes, bands of rock hundreds of kilometers wide, where the magnetic field points up, then down, then up again. These are magnetic stripes, identical to the ones found on the floor of the Earth's oceans near the mid-ocean ridges. They tell a story of plate tectonics, or at least of a crust that was forming while the dynamo was flipping its polarity. As the molten rock solidified billions of years ago, the iron minerals inside it, magnetite and hematite, aligned themselves with the magnetic field of the time. When the rock cooled, that alignment was frozen in place. It is a tape recording of the ancient dynamo. It proves, without a shadow of a doubt, that Mars was once alive with magnetism. Imagine the sky of the Noachian period at night. Because of the strong magnetic field, Mars would have had auroras. As the solar wind slammed into the magnetosphere near the poles, some particles would spiral down the field lines and crash into the upper atmosphere. They would excite the oxygen and nitrogen atoms, causing them to glow. Great curtains of green and red light would have danced over the northern ocean. A primitive microbe, looking up from a tidal pool, would have seen the sky ablaze with the electric fire of the dynamo protecting it. But a dynamo is a heat engine. It runs on a temperature difference. To keep the iron churning, heat must flow from the hot core to the cooler mantle. On Earth, this process is efficient. We have plate tectonics. The sinking of cold crustal plates into the mantle cools the deep interior, keeping the temperature gradient steep and the convection vigorous. Earth's engine is well ventilated. Mars is different. It is a stagnant lid planet. It likely never developed full global plate tectonics. Its crust is a single, solid shell. This means the heat from the core has a harder time escaping. It builds up. Or, conversely, the mantle cools too slowly. The temperature difference between the core and the mantle begins to equalize. When the gradient flattens, the convection slows. The churning stops. The plumes of iron become sluggish. The helical spirals unwind. There is also the matter of size. Mars has only 10% of the mass of Earth. It has less primordial heat trapped from its formation. It has less radioactive material, uranium, thorium, potassium, in its interior to generate new heat. It is a smaller battery. It runs down faster. The square-cube law is a cruel mistress. A small object has a large surface area relative to its volume. It radiates heat into space efficiently. Mars was destined to cool down long before Earth. Let us focus on the core's composition. Sulfur is the wild card. Sulfur lowers the melting point of iron. On one hand, this keeps the core liquid for longer, which is good for the dynamo. But it also affects the way the core solidifies. On Earth, the inner core is freezing solid, growing larger every year. This freezing process releases latent heat and light elements, which drive the convection. It powers the dynamo. On Mars, the specific mix of sulfur and iron might have led to a different kind of death. Perhaps the core didn't freeze from the inside out. Perhaps it froze from the outside in, or perhaps it stayed liquid but stratified, forming stable layers that refused to mix. Iron snow might have fallen in the deep, choking the flow. We are witnessing the vulnerability of a small world. The dynamo is a binary state. It is either on or it is off. There is no half-strength shield that lasts for long. Once the convection drops below a critical Rayleigh number, the magnetic field collapses. It does not fade away over millions of years. In geologic terms, it blinks out. It is a sudden failure of the planetary heart. The tragedy is that the biosphere on the surface has no idea what is happening beneath. The microbes in the Jezero Delta continue to divide. The rain continues to fall. But 2,000 kilometers down, the friction is winning. The viscosity is winning. The great, roiling loops of liquid metal are slowing down. The electric currents are dissipating into heat. The dynamo is stuttering. And when the field dies, the auroras stop. The green fire in the sky fades to black. The invisible donut of force that held back the sun dissolves. The field lines snap and reconnect, retreating into the crust, becoming the fossilized stripes we see today. The global shield is gone. The planet is naked. This was the turning point. The death of the dynamo was the gunshot that killed Mars. It wasn't an asteroid. It wasn't an alien invasion. It was thermodynamics. The planet simply ran out of the energy required to defend itself. It was too small to hold on to its heat. It is a sobering thought. Habitability is not just about being in the Goldilocks zone around a star. It is about having a restless, churning, violent interior. You need a living hell in the basement to have a paradise in the living room. As we leave the deep interior and ascend back through the mantle, we carry with us the knowledge of the disaster. The engine has seized. The shield is down. Above us, the atmosphere is still thick. The ocean is still blue. But the protector is gone. The solar wind, once deflected, now hammers directly against the top of the sky. The stripping is about to begin. The murder is in progress, even if the victim hasn't bled yet. We have witnessed the glory of the Dynamo, that churning engine of liquid iron that once generated the magnetic shield of Mars. But now, we must face the inevitable tragedy of physics. We must understand why the engine stopped. The death of the Martian biosphere was not a crime of malice. It was a crime of geometry. It was written into the very dimensions of the world at the moment of its birth. To understand the murder of a planet, we must look at the simple, brutal mathematics of size. Consider the two siblings, Earth and Mars. They were born from the same cloud of dust, forged in the same solar fire, and placed in the same neighborhood. But they were not created equal. Earth is a giant, a massive ball of rock, capable of holding onto its primordial heat for billions of years. Mars is a runt. It has only half the diameter of Earth, and only 1/10 of the mass. This difference is not merely cosmetic. It is the sentence of death. Attachment. In the universe, heat is life. A planet is essentially a spherical battery, charged with thermal energy during its violent accretion. Every asteroid impact, every collapsing layer of dust, trapped heat in the core. Radioactive elements like uranium and thorium act as a slow-burning fuse, adding more heat over time. But a planet is also constantly losing energy. It radiates heat from its surface into the cold vacuum of space. The fate of every world is determined by the race between the heat generated inside and the heat lost to the outside. Here, the square-cube law exerts its tyranny. As you shrink a sphere, its volume decreases much faster than its surface area. Volume is where the heat is stored. Surface area is where the heat escapes. Mars, being small, has a large surface area relative to its internal volume. It is like a cup of tea compared to a bathtub of hot water. The cup cools in minutes. The bathtub stays warm for hours. Mars was destined to cool down rapidly, bleeding its lifeblood into the black sky while Earth remained hot and molten. Let us journey back down into the deep interior to the era roughly 4 billion years ago. The Hadean Eon is ending. On Earth, the Dynamo is just getting started, ramping up for a long life. On Mars, the Dynamo is already struggling. The convection currents, those great roiling loops of molten iron we described earlier, are becoming sluggish. The heat flowing from the core into the mantle is slowing down. Why? Because the mantle is cooling too. As the whole planet chills, the temperature difference between the center and the edge diminishes. A heat engine requires a gradient. It needs a hot source and a cold sink. If the mantle becomes too warm relative to the core, Or if the core cools too close to the temperature of the mantle, the movement stops. The thermal buoyancy that drives the liquid iron upward falters. The fluid becomes still. There is also the chemistry of the abyss. The core of Mars is rich in sulfur. Sulfur is a volative element. It acts as antifreeze. It lowers the melting point of iron. This sounds beneficial. It keeps the core liquid, but it creates a trap known as stratification. On Earth, the inner core is freezing into pure, solid iron, expelling lighter elements into the outer core, which stirs the pot. On Mars, the sulfur might have prevented the formation of a solid inner core entirely, or it might have created stable layers of sludge that refused to mix. Imagine a salad dressing that has separated. The oil sits on top of the vinegar, and no amount of shaking can get it to move again. The iron snow hypothesis paints a haunting picture. In the cooling depths, tiny crystals of solid iron begin to precipitate out of the liquid mixture. They fall like snow toward the center of the planet. But instead of driving convection, this snow might have created a stable, stratified zone, a dead zone in the fluid that choked the dynamo. The helical spirals of current were disrupted. The magnetic field began to flicker. On the surface, the effect was likely gradual but catastrophic. The compass needles, had they existed, would have started to wander. The north magnetic pole would have drifted wildly, fragmenting into multiple weaker poles. The strength of the shield dropped from a roar to a whisper. The auroras, those curtains of protective fire, would have grown dim, retreating closer and closer to the poles until they vanished altogether. Then came the silence. The moment the dynamo stopped is not recorded in any chronicle, but it is the most significant event in Martian history. The electric currents in the core dissipated. The magnetic field collapsed. The invisible donut of force that held back the solar wind evaporated. The planet was turned off. It was now just a rock, passively orbiting the sun, with no active defense against the cosmos. The cooling extended upward, cementing the fate of the geology. On Earth, the crust is broken into plates that float on the mantle. They crash, dive, and recycle. This plate tectonics recycles carbon dioxide, regulating the temperature. It keeps the planet habitable. Mars, as it cooled, developed a stagnant lid. The crust thickened. It became a single rigid shell, locking the entire planet in a stone embrace. Time freeze. Without plate tectonics, the carbon cycle was broken. Volcanoes could still erupt, punching through the thick lid, but there was no subduction to pull the carbon-rich rocks back down into the mantle to be melted and recycled. The atmosphere was a one-way street. Gases could come out, but they couldn't go back in. And as the interior cooled, even the volcanic belches began to space out. The pulse of the planet slowed. The thickening of the crust had another side effect. It locked in the magnetism. As the last lavas of the Dynamo era cooled, they froze the direction of the magnetic field into their mineral structure. These are the crustal magnetic anomalies we see today in the southern highlands, the fossil magnetism. They are the tombstone epitaphs of the Dynamo. They say, "Here lies a force that once protected a world." Rate 100%, pitch 1%, Imagine standing on the surface during this transition. The change is invisible to the eye. The ocean is still there. The clouds are still there. But the balance has shifted. The wind from the sun, once diverted around the planet, now begins to touch the top of the atmosphere. The sputtering begins. The unseen assault on the air has started. The cooling of the heart was a one-way process. You cannot restart a planetary core once it has stopped. It is a thermodynamic arrow of time. Mars spent its heat budget in a glorious burst of early activity, forming the dichotomy, the ocean, the atmosphere, and then went bankrupt. It lived fast and died young. There's a profound lesson here for us. We exist on Earth only because our planet is large enough to stay hot. We are the beneficiaries of mass. If Earth were slightly smaller, or if its composition were slightly different, we too would be living on a cold, dead rock with a fossilized magnetic field. Mars is not a failed Earth. It is a normal planet that simply ran its course faster than we did. It is a preview of the ultimate fate of all terrestrial worlds. As the core solidified, or at least settled into its comatose state, the contraction of the planet began. As Mars cooled, it shrank. The crust wrinkled like the skin of a drying apple. These wrinkle ridges can still be seen on the plains today, scars of the planetary shrinking. The very ground buckled as the heat withdrew. And so, the stage is set for the execution. The shield is down. The dynamo is silent. The magnetic field lines have snapped and withered. Above the unsuspecting ocean, the sky is now naked. The sun, a relentless stream of particles, is about to begin its work. The cooling of the heart was the internal cause. The solar flaying will be the external result. The shield has fallen. The great magnetic dynamo in the deep, which once hummed with the power of a spinning planet, has fallen silent. The invisible lines of force that wrapped Mars in a protective cocoon have snapped and retracted into the crust, leaving the world naked against the cosmos. And now, the true violence begins. It is not a violence of explosions or impacts, but a silent, relentless theft. It is a crime committed atom by atom, over eons, by the very star that gave the planet life. We are about to witness the solar flaying, the stripping of the Martian sky. To understand this catastrophe, we must look to the sun. We often think of the space between the planets as empty, a vacuum, but it is not empty. It is filled with a tenuous, supersonic river of matter known as the solar wind. This wind is composed of protons and electrons, stripped from hydrogen atoms in the sun's corona and hurled outward at speeds exceeding 400 kilometers per second. It is a gale of radiation, thin but persistent, that scours everything in its path. When Mars possessed its magnetic field, this wind was deflected. It flowed harmlessly around the magnetosphere, like a river flowing around a stone. But now, with the stone removed, the river crashes directly into the bank. The solar wind slams into the upper atmosphere of Mars. It hits the ionosphere, the layer of charged gas at the top of the sky, with the force of a cosmic sandblaster. The process is known to physicists as sputtering. Imagine a game of billiards on a molecular scale. A high-energy proton from the sun comes screaming in from the void. It strikes a molecule of atmospheric gas, perhaps a nitrogen atom or a carbon dioxide molecule, hovering at the edge of space. The collision is violent. The energy is transferred instantly. The atmospheric molecule is kicked. It flies upward, overcoming the weak gravity of Mars, and is lost forever into space. One molecule is nothing. A trillion molecules is a whisper. But this process does not stop. It happens every second of every day for millions of years. It is a slow-motion hemorrhage. The planet is bleeding its air into the vacuum. We can visualize it as a comet-like tail of gas trailing behind Mars, a plume of oxygen and carbon ions flowing downstream with the solar wind. The planet is literally dissolving into the wake of the sun. The rate of this loss is staggering. Data from the MAVEN spacecraft, the Mars Atmosphere and Volatile Evolution mission, has allowed us to play detective at the crime scene. By measuring the escape rates today and extrapolating backward, we can calculate the volume of the theft. In the early days, just after the Dynamo died, the solar sun was more active, spinning faster and emitting more intense ultraviolet light. The stripping was ferocious. Mars may have lost 10 to 100 times more atmosphere per second than it does today. Consider the fate of the water. The Noachian Ocean was vast, covering the northern hemisphere. But water is fragile. Ultraviolet light from the sun strikes the water vapor in the upper atmosphere. It acts like a knife, slicing the H2 molecule apart. The hydrogen, being the lightest element in the universe, escapes easily. It floats away, riding the thermal currents into the dark. The oxygen, being heavier, is left behind. Where did the oxygen go? Some of it was stripped away by the solar wind, dragged out by the magnetic tendrils of the interplanetary field. But much of it turned downward. It had nowhere else to go. It reacted with the iron in the rocks. It rusted the planet. This is the origin of the red planet. The blood-red hue of Mars is the chemical tombstone of its lost water. The oxygen that once might have filled the lungs of a Martian biosphere instead bonded with the crust, locking itself into iron oxide for eternity. As the atmosphere thinned, the pressure at the surface began to drop. This is the critical threshold. Liquid water is a diva. It demands a specific pressure to exist. On Earth, at sea level, water boils at 100 degrees Celsius. But as you go higher, the boiling point drops. On the summit of Everest, water boils at 70 degrees. As the Martian air was stripped away, the Everest zone descended to the surface. Eventually, the pressure fell so low, below 6 millibars, the Armstrong limit, that water could no longer exist as a liquid at all. It could only be ice or vapor. The great northern ocean began to boil, not from heat, but from the vacuum. It evaporated into the thinning sky, only to be broken apart by the sun and stripped away. The lakes of Jezero Crater shrank, leaving behind concentric rings of bathtub scum, salts, and clays that dried and cracked in the sun. There is a specific piece of forensic evidence that confirms this story. It is the ratio of isotopes. Elements come in different weights. Hydrogen has a heavy cousin called deuterium. Deuterium has a neutron in its nucleus, making it twice as heavy as normal hydrogen. When the atmosphere is stripped, the light hydrogen escapes faster than the heavy deuterium. It is like skimming the foam off a cappuccino. The liquid left behind becomes denser. When our rovers measure the water trapped in Martian rocks, or the trace amounts of vapor left in the air, they find a deuterium to hydrogen ratio that is far higher than on Earth. It is enriched. This tells us, unequivocally, that Mars used to have a vast reservoir of water that was lost to space. The heavy atoms are the survivors, the ones too fat to fly away when the wind came. They are the leftovers of a great feasting. The thinning of the atmosphere also meant the end of the greenhouse effect. The carbon dioxide blanket, which had kept the planet warm enough for rain, was being torn to shreds. As the gas escaped, the temperature plummeted. The planet transitioned from the warm, wet Noachian to the freezing, dry Hesperian era. The water that didn't escape into space froze. It soaked into the ground, turning the crust into a permafrost cryosphere miles deep. The active hydrosphere retreated into the dark. Time freeze. Imagine standing on the surface during this long decline. The sky changes color. The pale blue or creamy orange of the thick atmosphere fades. As the molecules become fewer, the scattering of light diminishes. The sky grows darker, turning a deep, bruised purple, and finally, the salmon pink we see today, colored not by gas, but by the dust suspended in the thin air. The sun becomes sharper, harsher. The protection against ultraviolet radiation vanishes. The surface becomes sterilized. The loss was not linear. There were likely pulses of loss. During solar storms, coronal mass ejections, the sun would vomit billions of tons of plasma towards the planets. Without a magnetic shield, these storms would have ravaged Mars, stripping away massive chunks of the atmosphere in hours. It was a battering. The planet was being assaulted by the weather of the star. Time freeze. We also see the evidence of pickup ions. The neutral atoms in the upper atmosphere are ionized by sunlight, given a charge. Once they are charged, they feel the magnetic field of the solar wind itself. The wind sweeps them up, accelerating them to escape velocity. It is a magnetic trawler net, dragging the sky along with it. Is there anything left? Mars today has a pathetic atmosphere, less than 1% the density of Earth's. It is a wisp of CO2, but even this wisp is still leaking. Marvin watches it happen every day. The planet is still dying, geologically speaking. It is shrinking toward a vacuum state. If we do not intervene, in another billion years, Mars may look as airless as the moon. The tragedy of the solar flaying is that it was preventable. If Mars had been larger, like Earth, its gravity would have held onto the air more tightly. If its core had stayed hot, the magnetic shield would have remained. But Mars was too small, too cold, and too weak. It could not hold its breath against the gale of the solar system. This chapter closes with a vision of a world transforming. The rivers have stopped flowing. The ocean is a receding memory, a salt flat stretching to the horizon. The air is too thin to carry the sound of the wind. The silence has descended. The flaying is complete. The bone is exposed. The air is thinning. The shield is gone. The solar wind, like a relentless broom, has swept away the thick, warming blanket of the Noachian atmosphere. We are now standing on a world in transition, a planet caught in the throes of a violent metamorphosis. The pressure is dropping. The barometer had we one to consult, would be plummeting towards zero. We are witnessing the end of the liquid era and the beginning of the Great Evaporation. It is a time when the physics of water, the very substance of life, turns against itself. To understand the death of the Martian ocean, we must understand the tyranny of the triple point. Water is a shapeshifter. It can be a solid, a liquid, or a gas, but its ability to exist as a liquid is not a given. It is a privilege granted by atmospheric pressure. On Earth, the weight of the air presses down on the ocean surface, acting like a lid on a pot. It prevents the water molecules from flying apart. It forces them to huddle together in the liquid state. But as the Martian atmosphere was stripped away by the solar wind, that lid was lifted. Imagine standing on the shore of the Northern Ocean as the pressure falls. The temperature is dropping too, as the greenhouse gases escape. But the pressure drop wins the race. Suddenly, the water begins to behave strangely. It starts to boil, not from heat. The air is freezing, but from the vacuum. The chaotic energy of the molecules overcomes the weight of the air. The ocean turns into a cauldron of cold steam. Great plumes of vapor rise from the surface, curling into the thinning sky, only to be torn apart by the ultraviolet radiation of the sun. Attachment, attachment. This is the thermodynamic death spiral. As the water boils, it takes energy with it. Evaporation is a cooling process. Think of how sweat cools your skin. As the ocean boils into the vacuum, it sucks the heat out of the remaining water. The liquid that is left behind grows colder and colder until it freezes. A crust of ice forms over the boiling sea. The ocean is effectively sealing itself in a tomb of its own making. It becomes a sublimation engine, ice turning directly into vapor, bypassing the liquid phase entirely. The retreat of the water is catastrophic. The shoreline of the great ocean, once a stable boundary for millions of years, begins to migrate. It pulls back from the crater walls. It abandons the river deltas. It leaves behind vast, glistening flats of salt. These are the evaporates, sulfates, chlorides, gypsum. They are the bathtub rings of the dying world. Today, our rovers trundle across these white veins in the rock. They are the chemical ghosts of the water, the minerals that precipitated out when the solvent vanished. The landscape transforms. The lush gray muds of the Noachian dry out. They crack. Massive polygonal fracture patterns, kilometers wide, form on the surface as the ground desiccates. The clay minerals, formed in the gentle embrace of fresh water, stop forming. The chemistry shifts to the acid and the salt. The planet is becoming a desert. The dust begins to rise, no longer held down by moisture. The first global dust storms begin to circle the globe, scouring the rocks, erasing the delicate features of the riverbeds. But the water does not disappear entirely. It hides. As the surface becomes uninhabitable, the hydrosphere goes underground. The porous basaltic crust of Mars acts like a sponge. The water seeps down into the cracks, into the fractures, into the voids left by ancient lava flows. It retreats from the lethal low pressure of the surface into the dark, pressurized safety of the crust. Mars becomes a cryosphere, a world where the water is locked in permafrost, kilometers deep. This underground reservoir is vast. Radar data from modern orbiters suggests that there are still glaciers of water ice buried under the dust in the mid-latitudes, and perhaps liquid aquifers deep enough to be warmed by the planet's remaining internal heat. The life of Mars, if it existed, would have followed the water. The microbes would have migrated downward, abandoning the sunlit surface for the chemosynthetic darkness of the deep biosphere. The surface became a sterilized wasteland, but the subsurface remained a potential refuge. The transition period, the Hesperian Era, was defined by this struggle between the ice and the lava. Even as the atmosphere thinned, volcanoes continued to erupt. When hot lava meets underground ice, the result is explosive. We see the scars of this interaction in the chaos terrain. Vast regions of the crust seemingly collapsed into jumbled blocks of chaotic rubble. Imagine a layer of ice, a mile thick, buried beneath a layer of rock. Suddenly, a plume of magma rises from below. The ice melts instantly. The water flashes to steam or bursts out as a pressurized liquid. The ground above loses its support. It collapses. The water, released in a catastrophic flood, erupts onto the surface. These are the outflow channels, the Casse Valles, the Ares Valles. They are not rivers carved by rain. They are wounds carved by the sudden, violent release of the groundwater. These floods were biblical in scale. A wall of water, kilometers high and moving at hundreds of kilometers per hour, tore across the Martian plains. It carried boulders the size of houses. It scoured the bedrock clean. It flowed for weeks or months, dumping its load into the northern lowlands, perhaps briefly reforming a frozen temporary ocean. But the atmosphere was too thin to hold it. The water froze, sublimated, and vanished again. It was the planet gasping, trying to be wet one last time, but failing. The Great Evaporation was also a chemical tragedy. As the water disappeared, the remaining pools became hypersaline. They became brines, toxic, thick fluids rich in perchlorates. We see evidence of this in the blueberry concretions found by the Opportunity rover. These hematite spheres formed in groundwater that was acidic and oxidizing. It was not the sweet water of life. It was battery acid. Any life that tried to hang on in these shrinking pools would have needed to be an extremophile of the highest order. The sky above changed its character. With the water vapor gone, the clouds thinned. The great cumulus towers of the past were replaced by wispy cirrus clouds of water ice, and, eventually, dry ice, carbon dioxide snow. The thermal inertia of the atmosphere vanished. Without the water vapor to hold the heat, the nights became brutally cold. The temperature swing between day and night became extreme, cracking the rocks through thermal stress. We must visualize the silence of the sublimation. On a cold morning in the Hesperian, the frost on the ground does not melt into a puddle. It simply vanishes. It turns into gas and drifts away. The ground smokes with the ghost of the water. The physical state of liquid becomes a forbidden state, a violation of the new atmospheric laws. The planet has moved into a binary phase diagram, solid or gas. The middle ground is gone. Time freeze. The glaciers at the poles retreated, then advanced, then retreated again, driven by the wobbling tilt of the planet. But the net trend was loss. The water was being cycled through the atmosphere and stripped away by the solar wind. The inventory was shrinking. The deuterium ratio was climbing. The planet was distilling itself. And so the blue marble turned gray, and then, as the oxidation took hold, it turned red. The Great Evaporation was the final curtain for the surface biosphere. The stage was emptied. The actors, the rivers, the lakes, the clouds were dismissed. What remained was a skeleton of geology, a dried-out husk that preserved the shape of the water, but not the substance. As we look at the dry riverbeds today, we feel the phantom limb of the planet. The shape of the meander is there. The cut banks are there. The sandbars are there. But the fluid is gone. It is a landscape of memory. The Great Evaporation did not just dry the planet. It mummified it. It froze the history of the Noachian in place, preserving it under a layer of desiccation for us to find 4 billion years later. The water is waiting. It is still there, locked in the polar caps, buried in the permafrost, hiding in the molecular structure of the clays. It is waiting for heat. It is waiting for pressure. It is waiting for a terraformer's hand to melt it and bring the world back to life. But for now, the surface is a desert more absolute than any on Earth. The Great Evaporation has won. The liquid era is over. The ocean has evaporated. The shield has fallen. The sky is a tattered remnant of its former glory, stripped away by the relentless solar wind. By all rights, the story of Mars should end here, fading into a frozen, silent epilogue. But planetary geology is not a linear descent into death. It is a struggle. Even as the surface withered, the deep interior of the red planet held one final defiant reserve of energy. Before the silence took hold completely, Mars drew a deep breath of fire and attempted to resurrect itself. We are about to witness the era of the giants. We are about to witness the volcanic last gasp. To understand this final rebellion against the cold, we must look to the western hemisphere of the planet. Here lies a geological anomaly so vast that it deformed the shape of the world. It is the Tharsis Bulge. Imagine a continent-sized plateau rising up to 10 kilometers above the planetary datum. This is not a mountain range formed by colliding plates like the Himalayas. It is a blister. It is a colossal accumulation of lava, layer upon layer, built up over billions of years. The weight of this rock is so immense that it cracked the crust around it, creating the Valles Marineris, a canyon system that would stretch from New York to Los Angeles. Crowning this plateau are the kings of the solar system: Ascraeus Mons, Pavonis Mons, Arcia Mons, and the emperor of them all, Olympus Mons. Let us pause to comprehend the scale of Olympus. It is a shield volcano, similar in structure to Mauna Kea in Hawaii, but the comparison fails to capture the magnitude. Olympus Mons stands 21 kilometers high, 2.5 times the height of Mount Everest. Its base is 600 kilometers wide. If you placed it on Earth, it would cover the entire country of France. It is not a mountain. It is a geological planetoid resting on the surface of Mars. How did it grow so monstrous? The answer lies in the stillness of the Martian crust. On Earth, the tectonic plates are always moving. As a plate slides over a hot spot, a plume of magma rising from the mantle. It creates a chain of small volcanoes, like the Hawaiian Islands. The volcano grows for a while, moves off the hotspot, dies, and a new one is born. But on Mars, there are no moving plates. The crust is locked in place. The hotspot in the mantle remained stationary under the same patch of ground for hundreds of millions of years. The lava had nowhere else to go. It piled up and up and up. Now visualize the eruption. It is the Hesperian, or perhaps the early Amazonian period. The atmosphere is already thin. The planet is freezing. But deep below Tharsis, the pressure builds. The magma chamber, a subterranean ocean of molten rock, reaches its breaking point. The summit of Olympus Mons splits open. The caldera, a complex of collapsed pits 80 kilometers wide, becomes a lake of fire. In the low gravity of Mars, 38% of Earth's, the lava fountains are spectacular. They shoot kilometers into the black sky, unbroken by air resistance. They fall back in slow motion, painting the slopes in glowing rivers of basalt. But it is not the lava that matters for the biosphere. It is the gas. Magma is a sponge for volatiles. It holds dissolved carbon dioxide, sulfur dioxide, and water vapor. When it breaches the surface, these gases expand and explode into the atmosphere. This was the strategy of the planet. By erupting, the volcanoes were pumping greenhouse gases back into the thinning air. It was a geoengineering project of natural origin. As the Tharsis volcanoes roared to life, millions of tons of CO2 and H2O were injected into the sky. The atmospheric pressure rose. The sky thickened. For a brief geological moment, perhaps a few tens of thousands of years, the clock was turned back. The temperature climbed. The ice at the poles sublimated and reformed clouds. It is possible, just possible, that it rained again. Imagine the scene, a river of lava flowing down the flank of Olympus Mons, meeting a glacier of water ice at the base. The interaction is explosive. Steam explosions, phreatomagmatic eruptions, blast through the ice. Water flows once more in the channels, carved not by climate, but by catastrophe. The dormant microbes hiding in the subsurface cryosphere might have woken up. A brief Indian summer in the winter of Mars. The scale of Tharsis was so great that it did more than just change the weather. It changed the planet's orientation. This is the phenomenon of true polar wander. A spinning planet likes to keep its mass balanced. If you put a massive weight, like a giant volcanic province, on the side of a spinning top, the top will tilt until that weight is at the equator. This is exactly what happened to Mars. The Tharsis bulge grew so heavy that it physically tipped the entire planet over by 20 or 25 degrees. This shifting of the axis was chaotic for the climate. Regions that were once at the poles moved to the tropics. The ice caps had to migrate, sublimating in their new warm location and redepositing in the new cold zones. It was a period of global upheaval. The very ground moved under the sky, not through tectonics, but through the rebalancing of the planetary gyroscope. But the tragedy of the last gasp is that it was doomed to fail. The volcanoes were heroic, but they were fighting a losing war against physics. The magnetic field was still dead. The solar wind was still stripping the sky. Every ton of new gas pumped out by Olympus Mons was eventually grabbed by the sun, and thrown into the void. The planet was trying to fill a bathtub with the drain open. Furthermore, the sulfur acted as a double-edged sword. While CO2 warms a planet, sulfur dioxide can cool it. It forms aerosols, tiny droplets of sulfuric acid in the upper atmosphere that reflect sunlight back into space. The eruptions might have triggered a volcanic winter before the greenhouse warming could take hold. The sky would have turned white with haze, blocking the faint sun, plunging the surface into an even deeper freeze. And the internal heat was finite. The core was continuing to cool. The convection in the mantle was slowing down. The pulses of volcanism became further and further apart. In the Noachian, the eruptions were constant. In the Hesperian, they were frequent. By the Amazonian, they were rare events separated by millions of years of silence. The heartbeat of the planet was slowing to a bradycardic rhythm. Look at the lava flows on the plains of Elysium or Tharsis today. They are pristine. Some are so young, perhaps only a few 100 million years old, that they have almost no impact craters on them. They look like they cooled yesterday. This tells us that Mars didn't die all at once. It died in fits and starts. It shuddered. It tried to speak. But the silence between the words grew longer and longer. The ash from these eruptions covered the planet. It buried the old riverbeds. It created the vast, smooth plains of the northern hemisphere. It formed the Medusa Fossae Formation, a massive deposit of soft, easily eroded rock that wind has since carved into strange, ghostly yardangs, sculptures of dust standing in the desert. This ash is the cremated remains of the planetary interior. Eventually, the pressure in the magma chamber fell for the last time. The plume under Tharsis withered. The connection to the deep mantle was severed. The lava stopped flowing. The conduit in the throat of Olympus Mons solidified, plugging the volcano with a stopper of hard basalt. The giant fell asleep. The atmosphere, no longer replenished, thinned again. The water vapor from the last eruptions was stripped away or froze out. The brief, wet spell ended. The dust returned. The surface oxidation continued, turning the fresh, black lava into red rust. The planet had played its last card. It had thrown everything it had, its mass, its heat, its chemistry, at the problem of survival, and it had lost. Now, Olympus Mons stands as a silent monument to this struggle. It is a tombstone the size of France. Its caldera is empty. Its slopes are dusted with the red fines of the global desert. It is the highest point in the solar system, a ladder reaching toward a sky that is no longer there. It is a reminder of the immense power that once dwelt beneath the crust, and a reminder that even giants eventually fall silent. The volcanic last gasp was the final act of the active geological drama. The planet had transitioned from a dynamic, changing world to a static one. The wind still blows. The dust still shifts, but the land building has stopped. The engine is cold. The fire is out. Mars has entered the long, frozen stasis of the present. Day